There's an animal out there that carries enough venom in its body to kill a human being in under a minute. Not through a bite, not through a sting, just through contact. And yet that same animal lives with that venom running through its system every single day, completely unbothered. No antidote, no special treatment, no visible sign of distress. It just goes about its life like nothing unusual is happening at all. So what's going on? How does a creature carry something that lethal inside itself and survive it? The answer, like most things in biology, isn't simple. It's layered. It's the product of millions of years of arms races between predators and prey, between poisons and the bodies that make them. And once you understand the actual mechanisms at work, you'll probably look at venomous animals very differently. Because the real story here isn't about venom at all. It's about immunity, and why it's so much stranger and more specific than most people realize. Before we get into the biology, it's worth being clear about something. Venom and poison are not the same thing, and that distinction matters a lot here. Poison is harmful when you touch it or swallow it. Venom has to be delivered into the bloodstream, through a bite or a sting or some kind of puncture mechanism, to do damage. Most venomous animals could technically drink their own venom without dying, because the digestive system breaks down the proteins before they can enter circulation. But that's not the interesting part. The interesting part is what happens to the animals that are genuinely exposed to their own venom through their own tissues, through the act of producing it, through constant internal contact. That's where the real biology kicks in. Take the inland Taipan, which holds the title of most venomous snake on the planet by almost every measure. Its venom is roughly 50 times more potent than a king cobra's. A single bite carries enough to kill over 100 adult humans. And yet the snake that produces this venom is handling it constantly, from the inside. The venom glands sit just behind the eyes, connected to the fangs through a duct system. The tissue surrounding those glands is bathed in venom regularly. So why doesn't the snake die from its own product? Part of the answer is structural. The venom is stored in a sealed glandular environment, essentially isolated from the bloodstream by layers of specialized tissue. But that's only the beginning. Venomous snakes have evolved molecular-level resistance to their own toxins. This is one of the genuinely remarkable things in all of biology. Many snake venoms work by targeting specific proteins in the body, blocking receptors, interfering with clotting, destroying cell membranes. And in their prey, those proteins are wide open, completely vulnerable. But in the snake itself, those same proteins have been modified. The receptor that the venom normally locks onto has a slightly different shape. The venom molecule arrives, looks for its target, and can't get a clean grip. It's like a key that's been filed down just enough that it no longer fits the lock. The snake evolved the lock at the same time as it evolved the key, and it kept changing both in parallel. This is called molecular resistance, and it's been documented in multiple snake species independently. What makes it especially striking is that it didn't happen once. Several lineages of venomous snakes evolved very similar resistance mechanisms separately, which tells you something important. The selection pressure is so intense that evolution keeps arriving at the same solution. If you're producing something that's lethal, you either develop resistance or you go extinct. There's no middle ground. Honeybees run into a version of the same problem. Bee venom contains a compound called melittin, which is the primary cause of pain in a bee sting. It punches holes in cell membranes. It's extraordinarily effective at causing damage in most animals. But bees themselves produce and handle melittin constantly without destroying their own tissues. Part of this comes down to storage and compartmentalization. Venom is held in a highly acidic sac that keeps it in an inactive form until it's delivered. The cells that line the venom sac have specialized membranes that resist melittin's effects. The bee's own cells are simply not as vulnerable to the compound as your cells are. And then there's the platypus, which takes things in a genuinely weird direction. Male platypuses have venom spurs on their hind legs, and they produce a cocktail of compounds that causes excruciating pain in humans. The pain is resistant to morphine. It can last for weeks. And here's the strange part. Platypus venom evolved from genes shared with immune system proteins. It didn't come from nowhere. The building blocks were already there in the genome, repurposed over time into something entirely new. The platypus itself is resistant to its own venom, but the resistance isn't just molecular. The immune system appears to actively tolerate the compounds rather than treating them as foreign invaders. That's a key concept here. Immune tolerance. Your immune system is constantly making decisions about what to attack and what to leave alone. It learns to ignore your own tissues, which is why autoimmune diseases are so damaging when that system misfires. Venomous animals have essentially extended that immune tolerance to include the compounds they produce. The body recognizes its own venom as self, not as threat. The immune system never launches a response against it because it was trained from birth, and possibly from before birth, to treat those molecules as normal. This isn't unique to venom, by the way. It's the same principle behind why you don't attack your own stomach acid or your own digestive enzymes. Your body makes plenty of things that would hurt you if they landed somewhere wrong. Compartmentalization and tolerance are the solutions evolution landed on. Now consider the mongoose, which doesn't produce venom at all but is famous for fighting and surviving cobra bites. The mongoose has independently evolved a modified version of the acetylcholine receptor, the same protein that cobra neurotoxins target. In most animals, cobra venom locks onto that receptor and blocks nerve signals from reaching muscles, causing paralysis and eventually suffocation. In the mongoose, the receptor's binding site is shaped slightly differently. The venom lands, can't get traction, and the mongoose walks away. This evolved in an animal that doesn't even make venom, purely because it lives in environments where cobra encounters happen regularly enough that resistance became a survival advantage. Honey badgers show something similar. They raid beehives and get stung hundreds of times. They get bitten by venomous snakes, sometimes enough to lose consciousness temporarily, and then wake up and keep moving. The honey badger's venom resistance comes from a combination of thick skin, which slows venom penetration, and modified receptors that reduce sensitivity to neurotoxins. It's not complete immunity. The honey badger is still affected, still feels it, but its threshold is dramatically higher than almost any other mammal its size. And critically, it recovers faster, because the cascading damage that venom usually causes is blunted at nearly every step. What about the human side of this? Why can't we do any of it? The honest answer is that we've never lived under sufficient selection pressure to develop these specific resistances. Venomous animals are dangerous to humans, but historically, encounters were rare enough that they didn't drive evolution in a meaningful direction. A species develops resistance to a specific threat when that threat kills enough individuals, consistently enough, over enough generations, that the survivors with better resistance reproduce more successfully. Snakes evolved resistance to their own venom because every individual that failed to develop it died. The selection was absolute, and it operated over millions of years. Humans face snake bites and bee stings, but we also develop tools, shelter, fire, and learn to avoid dangerous animals. We externalize the solution, like we always do. We developed anti-venom instead of evolving resistance. We learned which animals to stay away from. It's the same pattern as the water story. We're remarkably good at building external solutions to biological problems, and remarkably slow at evolving internal ones. That's not a weakness exactly. It's just a different strategy, and it has worked well enough that we're still here. So the next time you read about someone dying from a box jellyfish sting, or a taipan bite, or a cone snail puncture, remember what's actually happening at the molecular level. The venom is finding targets that evolution left completely exposed, because there was never any pressure on humans to armor them. And somewhere nearby, the animal that made that venom is carrying it around by the milligram, completely unaffected, because its entire cellular architecture has been shaped over millions of years to treat its own deadliest weapon as something entirely ordinary. It produces the thing that could kill you in seconds, and its body just files it under normal. That gap between what venom does to you and what it does to the animal that makes it is one of the more extraordinary distances in all of biology.